Welcome to the second lecture of the Mathematics and Statistics of Infectious Disease Outbreaks. My name is Michael Höhle, and I will continue in this lecture with the material that Tom has covered. So I'll start to share screen, going to the lecture slides, and we'll take it from there. Okay, so here are the slides. All right. Okay, so we will cover three topics here. We will look at models which Tom covered in his first lectures, the Reed-Frost model, the deterministic SIR model, and the stochastic SIR model in continuous time. This is what we will cover. And I will do 3 video lectures so it won't be one large file, and that you also have the opportunity to watch whenever you're ready parts of it. So let's return to the slides. Let's talk about the Reed-Frost model. So as Tom covered, the Reed-Frost model is a compartmental model where you divide the population into susceptible, infectious, and recovered, where from an infectious disease modeling point of view, you don't really distinguish between if people have recovered because they are dead, they're isolated or immune. The important part is that they don't contribute to the disease spread anymore. And this is a classical model for person to person or animal to animal or plant to plant transmitted disease. So we will look at a closed population which initially has N susceptible and M infectious individuals. We will say this is what the initial condition at time 0. And then we will model the dynamics of the disease in discrete time, where each time step of the model corresponds to one generation time. So let's say a generation time means, and Tom will cover more of that in his lecture, the generation time is the time from when the primary case becomes infected to the secondary case that he or she infects will become infected. That's the generation time. We will here assume that it's a deterministic generation time, and it will last a certain amount of time every time, and one time step in our discrete time Reed-Frost model will correspond exactly to this generation time. So what we have in each step of the simulation, it is adequately described by a discrete time Markov chain, where we say, well, given that we know the current number of susceptibles and the current number of infectious, we can simulate how many new infections we will get in this one time step ahead. So we will use the small letters here to denote observed quantities, and Y capital letter is a random quantity, a stochastic variable. And we will here say that it's described by a binomial distribution. So you have that the number for each of the susceptibles, we will look at what is the probability that this individual will be infected in the next time step. And this is a quantity which depends, of course, on how many current infectious individuals there are. So this will be the probability for this, given that we assume that the probability to meet between two individuals within one generation time, that is described by W. So actually here in the first exercise, you're supposed to show theoretically that this is the correct probability that one susceptible individual will be infected in one time step. So this can be derived, and then we say, well, they are going to be independent of each other, how they are going to infect each other within the one time step. But of course, for each time step, this probability depends on the number of currently infectious. And we will then simply count off how many times this occurs. So this is yt plus 1. And given that we know yt plus 1, we can also, and this is a simply deterministic quantity, we can deduce how many susceptibles are left in the next stage. That's simply the number of current susceptible individuals we have minus the number of individuals which became infectious in this time step. So this is simply bookkeeping. So the only random quantity we need to worry about is the yt plus 1. And we can then look at properties of this model. And Tom described some of it, and one of them was here the final size of the epidemic, which was simply the number of additional infected people we get beyond this M initially infected persons or animals or quantities, individuals, whatever we're looking at. So this would be Y1, Y2, Y3 until the end of the epidemic. And actually, and that is something you can show that this can be computed analytically for small n, say n below 30. And if you want to look at the equations for this, this is in this book, which I've mentioned previously. You see I have a bit of a hard time to try to get the background part connected with the book. So in this book here, you can show there are some equations for it, how to do that. It's not so important, but they are numerically also difficult once you have n bigger than 30. But here for this case with 20 initial susceptible, 1 infectious, and contact probability of 0.02 per time step, we see that on almost 70% of the cases, this initial infectious is not able to infect any others. A few times he or she is able to infect 1, 2, 3 additional ones, but there will never be a large outbreak in this case. Interesting now, what happens if we vary W? We can compute that in the simple case, but what if the population is a bit bigger? Then our analytical equations are not going to work anymore, but what we can resort to is simulation. And I will show in a few slides that how we can simulate from this. But let's look at the results first. So we'll now look at a bit bigger population with 100 individual and 1 initial infectious. So 100 susceptible and 1 initial infectious, 101 persons in total in the population. So here is our W. If it's 0.01, we see that the epidemic almost always dies out immediately, or it will only be a minor outbreak. If we start to increase the W, we see that we have now a certain proportion here, which, and there's theory for that, this is actually going to be some kind of normal distribution limit here to this quantity. So you see the mass moves away, the probability that you will have a minor outbreak will be smaller and smaller, and here this will be bigger and bigger, and it will move to the right. So it will always become bigger and bigger here, and the larger W is, now here you have almost all are infected at the end of the outbreak, and there's only a very small probability that this initial infection is not going to infect anyone, and the epidemic or the outbreak is going to die out quickly. So this is something we can look at. These are properties which we can investigate. And of course, there's always the analytic and the simulation, but the simulation has the advantage that even in very complex models, maybe even much more complex than the ones we are looking at, we can still do such quantities that as the final size and other things. So let's look at how we simulate from such a model. Well, the key to this is, of course, that we know this binomial distribution and Markov chain thing. So here is the R function, which I showed. You can either look at the code which is provided on the web page for the simulation, or you can also, now I set up a GitHub where you can also find the code for all of this. And here you see, and I will go, instead of showing this here on the slide, I will try to show this in RStudio so you at least once see how I work with this, or how we can work with that. So let's change the sharing to RStudio. And like this. All right, so we're here now in the final size of the Reed-Frost model. We have here the function that I just showed on the slide. So we have N is the number of initial susceptible, M is the initial number of infective, W is our probability that they will meet in a given time interval, and this is the number of epidemics which we will concurrently simulate, right? So the important part is that we can simulate several epidemics jointly. We will set up matrices where the initial value is simply here an initial number of susceptibles, and here we have the initial number of infectious in the first time step 0. And now we will always simulate as long as there's still susceptibles and still still infected. We will keep simulating. So we look at if there's still something to do, and of course there is in both cases. They're still susceptibles, they're still infectious. So we can sample from this. So what we will do for each, and we will do this not for one epidemic at the time, but we can do this vectorized, which speeds up the simulation quite a lot. So what we look at, are there still susceptible left? Otherwise, we will have a 0 because there will be no new infectious. And then we will use this quantity which we have from our Markov quantity. We will say, okay, how many susceptibles are there at the moment? So 100, 100, that's the population size. So we'll do an entire vector of 3 simulations. And for each, we'll look at what is the probability that each of them will be infected. Sorry about that. Like, sorry, I should put in a value for this, like this. Let's try if it's not working now. Right, so this is the probability that they will, for each of them to be infected within the next time step. And then we will simply draw from a binomial distribution, right? So we will simply draw some values at random from this, like this here. So here will be 4 new infectious, 0 for the other one, and 3 for the last one. If you're interested in trying to find out what is this function that I'm using, so here's our binomial function. It is simply a function to draw random variables from the binomial distribution and how many and with what probability. And you can, that's the special thing here, you can provide for this one and this one here, you can provide vectors, and then we'll simply use these and draw from them simultaneously. So we can do it like this. So we have our yj here, 1, 3, 1. And then we will update the number of, sorry about that, we will update the number of susceptibles, and then we have our numbers here. Then we already know that in the next step, we still have something to do. We will draw a new number of infections, 181, and then we will do the bookkeeping again. And we can look at xj, and we get our numbers here. And then we can say, okay, we will continue with all of that until the end. So probably we can now see how many are there left. Well, there were 18, 13, and 15 left at the end. And that's how many, then we get the final number of the size of the epidemic in each case is just n minus xj as calculated above. So we get here the size of the outbreak. So having this as a function, we can also, we don't need to do this manual step by step as I showed here. I can do it like this. N was 100, M is equal to 1, W we said 0.02, and samples, let's take a few more. So 1,000, for example, and then I get here all the final sizes from all of this. And I can, of course, also say I'm going to take that as a factor, and levels are between 0 and 100. And then you get the distribution here for how many of the simulations cover each of them. And if you want to, you can also say prop.table. And then you get the probability distribution if you want to, right? And of course, you can also plot this if you want to, or take a bar plot if you want to. Here is the result for this. Alternative is the bar plot. Or you can, of course, also use the ggplot if you like that one more. So you see here we have some probability for some probability that the outbreak will die out immediately, and then we have some of probability that we will have a major outbreak. And that's all of this is done by simulation. So this is your first example of simulating from a read frost model. Okay, so what we now have is that we are able to artificially simulate data, but of course we also observe data in the real world. And what we need to do is try to infer the parameter, which we here sort of said, okay, we know it. How do we do that? Well, for that, I'm going to return to the slides. practice. And let's go here. For that, we have to look at some statistical principles like likelihood estimation, which is something which is not a prerequisite to know about this course because there was no initial knowledge about statistical methods used, but this is a principle which may be known to you, but for some of you it may not be, so maybe you want to catch up on some of these concepts by reading it a bit, but for this course only the concept is important, namely you have statistical models, you have parameters, and you have data, and you want to infer the model parameters from the data. So what you do is you say, okay, I'm going to have a statistical model, something which implies distributions, parameterized, so it's a parametric model. It has parameters, and what we set up is to say, well, given these parameters, our data have a certain likelihood, or they have a certain probability to occur, or in a continuous case, it can be described by a density, but let's take the simple case that where we have a discrete model. And what we're going to say is, well, we're going to have a target function which says how likely are the data we will see as a function of the parameters. And that's what we're interested in. And what we simply do is we say, well, y is our random quantity, and what we did observe is this small y. What's the probability of this to occur given that the parameters are theta? Right? So here it's simply we have to make a model for the joint probability of all those random quantities which are part of our data, and we have to formulate a model for the joint probability of all of this. So that will be one task to do for also the Reed-Frost model. But what we will then do is to formulate this as a function and say, and turn it in some sense around. What we assume is that we fix the data and say, these have been observed, they are fixed, and now we want to say which parameters make those data that we have observed as likely as possible. So because we have seen them, we say we want the parameters to be such that what we have seen is as likely as possible. So this will be considered to be a so-called likelihood function. So you can say we reverse the arguments. Y is considered in some sense as fixed, and theta are the parameter or the parameter vector which we try to infer, and that's what we want to go to do. And then the point in parameter space, which is sort of covering the support of theta, that maximizes this likelihood function here. That's what we call the maximum likelihood estimate. So how does this look for our Reed-Frost model? Well, you can use again the binomial probability to set this up, and you will see that we can provide an expression for this likelihood which looks as follows, which is simply a product of binomial terms originating from this binomial likelihood we had, where we have that each of these PTs is something which again is related to this probability that we have. Of course, important is that we need to know x naught, because that's something we can condition on. And of course, we may not only be interested in the point estimate of W, but also something quantifying the uncertainty around it. So that is the possibility. So before trying to go through this for a data example, let's look at this expression here. How does it originate? So what I tried to do here is to go to the preview. For the other one, here it is. So here's what we needed to do is to formulate a likelihood for the complete data. So what we want here is this quantity here. We want to figure out how should this look in our model. Theta in our case is the W, and what we thus need to do is we need to formulate the joint probability distribution of all these observations, and all of them which could vary where the number of infectious in each state. So that's yk to y1, and we will condition on this part here y1, y0, and x0, because these were considered as given. So now there's the law of total probability, which you can use to decompose this joint probability always into the one leading term, the yk, given all the others, times the probability of this part here. And then you can again take this probability here and divide that into k, sorry about that, it should be k here, k minus 1 given k minus 2 down to the rest that you have, right? And then you have your 3 dots, and that's the last term is going to be that one. So what you see now here, you have a probability where you have all kinds of terms in between, which you supposed to remember because it could depend on that, but that's when the Markov property kicks in and says, well, and you saw that from the Reed-Frost model, you don't need to know the entire past. If you know just the immediate past, namely at yt, you just need to know yt minus 1 and xt minus 1. All the previous past is not going to matter. So all these very lengthy terms here, they cancel. You just need to remember the immediate past. So what all of this reduces to is simply a product of individual terms where you have to specify the probability distribution for yt given yt minus 1 and xt minus 1. And the xt minus 1 is actually not a random quantity. This is something which you can simply deduce by bookkeeping, right? So this is what we had here. And then we knew each of these terms here, that's simply a binomial probability. So what we will, at this stage here, will we use a binomial probability mass function. So that's the xt minus 1, yt out of xt minus 1. Then we have here this pt term, which is given here as a function of v. So all of this here is always a function of v, right? That's what is the interesting part, because that's the v, the w, that's the one we actually want here. Okay, so we have this, and now we could even take the log of this and then try to find, differentiate that, solve it equal to 0, but that's going to be difficult here because you have a log and here's the w hidden, so it's actually not possible to solve this easily by analytic methods. So what you need to do is actually to optimize this using numerical methods. So I'm gonna change my share again to back to the slides. So this, which I just showed, sorry. Yes, so we are back here. So this was the term that I just showed. Hang on, I can show a bit here. This was the part which I just showed. Just with a different index, I used 1 here and k here, and then of course you have to always these move a bit, but that's the same. It's the same result. So we know now this is the equation, and let's look at this from an example. So there's an example from a measles epidemic in St. Petersburg in a small community. You had that in the first generation there was 1 initial infected, then it was 4, then it was 14, then it was 10, then it was 1, and then the epidemic died out because there was no infectious anymore. There it was 0. So that's when it stopped. And what we will assume now is that all susceptibles got infected. We don't for sure know how many it was, but let's assume it was all the susceptibles which got infected. So that would be the 4 plus 14 plus 10 plus 1. That would be 29. That's one guess at how many. Of course, the community could have been larger. We'll look at that in just a while, but let's assume initially it was 29 susceptible and 1 infected. And what happens then? And that's what we're going to do, what we want to do with data. So we set up here our likelihood functions. So this is just here, you see you have the binomial terms. Here we always remove the first element because that's the time 0, which we don't need for this. And then please note that I'm not going to use the w directly for this function. I'm using log it of w, and that's instead, this is just, so this is, I'm looking at, sorry about that, like this. So I'm looking at w1 minus w and then the log of this. An advantage is that this quantity here is if w is between 0 and 1, so w is between 0 and 1, this quantity here is going to be between minus infinity and infinity. So it's unrestricted space, which means it's a bit easier to optimize, but actually it's not necessary to do this. Probably the function would work still, but I'll do it like this. And here I just take the p logos is just the inverse of this function, which is x of w divided by 1 plus x plus w. This is just a small numerical trick to do the inference. Possibly it's not even necessary, but these are standard functions which are implemented in R. If you use another programming language, you might need to hand code this, but actually you can simply also, it would be easier to simply use w here. Anyway, this is our likelihood function. X and y are data, and this is the parameter we want to optimize for. And then we have a key in the data. We do the bookkeeping here. We always figure out how many susceptible are there at each date in order to have a y and an x vector. And here's the call to the optimization function, which is called optiminar. There are also others, but this is the one I will be using here. The function we want to optimize is the log likelihood function, and we will start with a parameter of 0, and 0 means here on the logit scale means 0.5 on the W scale, right? We will use some kind of optimization routine, doesn't matter how much, which one it is. And then we have here the FN scale argument means that optim is what it's doing is a minimization problem, but here I said we want to maximize the likelihood function such that the parameters are chosen such that the data that we actually seen are as likely as possible. So that's a maximization problem. So this is just a trick here to turn the minimization into a maximization problem. And then we get a result. So mle.par is the result we got, and then we just back transform it, and we get here our estimate for W on the data. And if you know a bit more of statistical theory, you can also derive uncertainty intervals, confidence intervals for this quantity, but I'm not going to cover this as part of the current lecture. So what we can do then is, as I said, the 29, the initial number of susceptibles, we assumed that it was all of the infections, all of the population got infected, so it's 29 initially. But of course, that is not sure. What about, maybe it was more, right? So we're going to take this as a second parameter, which we actually need to optimize for. So what we're going to do is take a profile likelihood-based approach. We say, okay, let's try with 29. That's what is the value of the log likelihood that we will get. Then we will take 30 and study what is the value of the log likelihood which we will get, and so on. And you see, this is a declining function. So actually here with the 29, that's the log likelihood, the best likelihood we will get by always taking this parameter as fixed. We will then optimize the W, and then we'll see what is the log likelihood in this case. So this is the maximum value here with the 29. So we're going to stick with the 29 as our maximum likelihood estimate for X naught. Right. So that was, in short, a study of the Reed-Frost model and its simulation properties and its estimation in this model. Right. I'm going to take the deterministic SIR model as part of the next lecture. So I'm going to stop recording here. And let's see how I'll do that. End meeting. And see you back in the next lecture.